Hi, everyone. First of all, thank you to the hosts and thank you everyone for coming out. So I'm really excited to be here giving a talk on open table format interoperability with Apache Xtable. So a little bit about myself. Previously, I worked at AWS EMR, where I was on the data lake team, integrating popular table formats like Apache Hoodie, Apache Iceberg with EMR Spark offering. And very recently now, I joined a data startup called OneHouse, where I'm solving problems in the realm of streaming, ingestion, table services, and now Apache Xtable. So before we even talk about Xtable, I do need to cover a couple of building blocks to really explain or give context as to why Xtable even exists and the problem it's trying to solve. So this is just a quick agenda of what we'll be talking about. In terms of questions, I actually will take them after Anand finishes because this is a two-part series. So I'll be talking about Xtable, at least from the open source perspective, and then Anand will be talking about Xtable in production at Microsoft at scale. So I don't know how many people here can relate to the images above, but building a data lake and operating it at scale is very frustrating. It can result in tears. And I find that even for people in the space, the term data lake or data warehouse or lake house, it might sometimes sound a little bit like marketing jargon. So before we even kind of dive a little bit deeper, want to give a little bit clarity as to what these terms mean. So traditionally, a database system basically tied two core entities, that being storage and compute. Computation was primarily done by taking SQL, transpiling that into some optimized plan that would then scan the actual data that sat within the local disk of that compute node. And these systems had very mature features in terms of cataloging, which essentially is mapping out maybe a collection of files to some table identifier, things such as resource management, access control, etc. So they were a very robust product, but the main biggest issue for users was when I wanted to scale, let's say, compute and storage independent of one another, you couldn't do this in this kind of architecture, and it became very expensive. Then another architectural pattern came out in the early 2000s with the Hadoop ecosystem. So essentially, data lakes became synonymous with taking open files, something like Parquet or text files, and just dumping it on a distributed file system, something like HDFS, and eventually it became cloud storage like S3. But I think the biggest issue with the data lake was that it was ahead of its time, and it didn't have a lot of core database guarantees that we got with traditional systems. So things such as taking your collection of files and having some aspect of atomicity, things such as being able to perform table maintenance. So as your files grow in size, are there operations to clean out, those files after a certain period of time? So the current architecture today now is a mix of these two paradigms, both the warehouse and the lake, which is now this term lakehouse. Essentially, it is an unbundling of the database system. So today, users can choose their compute engine, whether that be something like Apache Spark, Apache Flink in open source, or they can use a vendor solution like Microsoft Fabric or AWS EMR. You can choose the ways in which your data is actually serialized in some open file format, something like Apache Parquet or Apache Avro. And you can choose the actual service in which where you want to store these files, something like S3 or Google Cloud Storage, Azure Data Lake Storage, etc. But the focus of this talk is primarily focused on the middleman, essentially these table formats that sit between the compute engine and storage, and the guarantees they give in terms of being able to support transactions. So at the core, these table format projects, I think this audience is pretty familiar with Iceberg, but at least for like Hoodie and Delta, they all have these metadata files that sit on top of your actual data files. And these metadata files are essentially adding asset transactions to the data lake. So what I mean by this is being able to support atomic writes. So when I do a write to my table, is this an all or nothing operation? Supporting things like concurrency control. Say I have two writers writing to my table. Do I employ certain strategies for maybe locking on the table? Do I employ a strategy like doing optimistic concurrency, where I fail one writer and ask it to retry and fetch the latest state of the table? Supporting things like time travel queries. So as I'm making changes to my table, maybe I care about the specific state of the table at a certain period of time. Things such as giving the engine maybe statistics in terms of column statistics or partition statistics. so that my engine can actually fetch the files only relevant to the query. There's a lot of features, but I can't really go into all of them. But I think the core thing I want to really emphasize is that if you were to look at these table format projects, let's just say you want to create a hoodie table, a Delta Lake table, or an iceberg table in some cloud storage like S3, it really is just these metadata files that are sitting on top of your data files. And usually the standard in the industry now has become, at least for data files, Parquet. And each of these projects have, their own unique way of representing this metadata. So as you all probably know, for Iceberg, it's a tree-like structure where you have a list of snapshots, each snapshot referring to a list of manifest files, each manifest file referring to a list of data files for what was added or deleted in that operation. For Hoodie, it's a notion of basically a timeline where as you're making commits, there's a notion of a file group, and a file group is nothing but just a collection of these file slices that have a reference to a Parquet file and a log file for the actual appends. And Delta Lake has a notion of a transaction log, which is just basically a sequence of these JSON files. I think there's also a notion of checkpoints that kind of aggregate these JSON files over time so that you don't have to read a bunch of small JSON files. So I won't go into all these examples because I think that also would take a lot of time. So let me leave you with one at least. Say you're a data enterprise and you have data engineers and they're using Apache Hoodie because they've heard of its great capabilities when it comes to ingestion and streaming. But in that same organization, you have your analysts and they want to use something like Snowflake because it has a very good use case for business insights and reporting. But Snowflake is very much supporting, or at least, integrating very well with Iceberg. And you want your analysts and your engineers to have the same view of the data. And even to add on to that, you have your data scientists, and they enjoy using the experience of maybe Databricks' notebooks with engine like Photon because it supports very fast reads with Delta Lake. So if there was a way for us to essentially mix and match formats without having to actually copy the underlying data files, but just keep track of metadata, between them, it would open a lot of use cases in terms of the engines you can actually bring, to your data. So essentially, the solution is Apache XTable. So to clarify, XTable isn't just another table format. It is a omnidirectional converter that handles the job of basically converting metadata between each of these table format projects, whether it be Hoodie, Delta, or Iceberg. So just a quick timeline of events for how XTable came to be. Essentially, the company I work at, OneHouse, had made an internal product known as OneTable. We did a co-launch with Microsoft and Google to have this open source. And then more vendors and companies got interested in the project. So we were able to donate this to the Apache Software Foundation. And I think the big news last year was Microsoft Fabric and Snowflake had a partnership. So essentially, there's a product in Microsoft known as OneLake. And under the hood, it's using XTable to handle the conversion between Delta Lake to Iceberg. So I'm really excited for Anand's talk because he'll be speaking about how they're using OneLake and XTable at scale at enterprise level. So you might be asking though, how do you as a user go and actually interact or use XTable? Essentially, you'll construct a YAML file, and this YAML file will have three core things. So the first being, what is the actual source format that you're currently working with? What is a target format, or basically the thing you want to convert to? And then finally, usually a cloud storage path to where your table is located. And if, for example, let's just say I had this hoodie table over here, I can then download the XTable utilities bundle jar, pass that YAML file that I created, and essentially I can run this XTable jar either on my local machine or on a remote cluster, but it will handle the job of creating metadata for not only just, obviously Hoodie was already there, but Delta and for Iceberg. And the benefit of that is now I haven't gone through any complicated migration process of recreating data files or recreating tables. All I've done is just created metadata, and essentially I can bring an engine, something like Apache Spark, and be able to interact with that same data with all these formats, as you can see with Spark.readup format. So now we'll be looking a little bit at the internals. This slide, I think, has a lot of information on it. So the following slides will be looking at individual slices of how this conversion happens. So the three core components are there's a conversion source, a conversion target, and a controller that orchestrates the entire process. So a conversion source is nothing but essentially breaking down what a table format is into like building blocks. So each format has a way of representing things like schemas, which is basically the structure or the types of your table. Things such as partitions, which is the way in which that table format is actually distributing data on storage. Things like we talked about a little bit earlier, column stats or partition stats. The actual pointer to how it's representing a data file. So maybe some path on storage to where that file is located, as well as what file format it's in. And then commit extractor is nothing but, Iceberg has a notion of a snapshot, but he had the commit. In Delta, there's a transaction JSON. So being able to extract the actual operation that happened on the table. And what I really want to leave you here with is that this is a very easy, extensible interface so that in the future, other table format projects outside of the big three can go and extend this interface so that then they can also interop between Hoodie, Iceberg, and Delta. The conversion target is nothing but just a mirror of source, but instead of reading, now you're writing to your target format. So essentially, you also go and implement this interface and then, similar to what I mentioned before, write out how that table format represents its schema, partition, stats, etc. And finally, is the kind of the brain of how XTable works is this conversion controller. So this is basically handling the entire sync process. It handles things such as obviously taking in the user's configurations, initializing each of the table format clients, but it also handles things such as state recovery. So say I'm running the sync and I have like, let's just say 5 commits from Hoodie and there's a network failure. I should be able to keep track of what was the last sync instant and then be able to pick up from that point and continue on in my metadata conversion. Also, it has modes for doing a full sync or incremental sync. So say I've already synced 5 commits in my table, and now 3 new commits come. I don't want to have to look at the entire timeline of events. I should just look at what's changed between them. So the biggest question we sometimes get at OneHouse is why build something like XTable? So for OneHouse, we're interested in building what's known as a universal data lakehouse. We want to be able to consume from many types of data sources, whether that be database logs, Kafka streams, or even just raw Parquet files sitting on S3. So we have a high quality, very fast ingestion product, and then we allow users to specify what is the storage format they want to use, whether that be Iceberg, Delta, Hoodie. And the benefit of that is now that it's in one of these open formats, it opens a bunch of use cases for the actual engines you can bring. So you can use Snowflake with Iceberg for BI reporting. You can use ML, you can use Databricks as engines for ML and AI use cases. You can use something like Flink with Hoodie for streaming. And we handle the hard job of at least optimizing your tables. So running table services like compacting your data files so that they're better for query performance, things such as cleaning and archival so that as this metadata grows, you can start to expire or remove it after a certain threshold. And also low-code pipelines. So building a data lake is very expensive because you have to hire a bunch of engineers, each of them familiar with a particular ecosystem, and usually have to stitch together a bunch of PySpark or Scala scripts. But in our product, we ideally want it to be as easy as possible for people to build data lakes or lake houses, say. So in terms of the roadmap, we already have the major projects supported in terms of Hoodie, Iceberg, and Delta, and we test this out with a couple of popular open source and vendor engines. I think the way in which the industry is moving now has been very much in the catalog space. So we believe, at least at OneHouse, that there won't be even one catalog where all the data will be essentially interfaced in. We want to be able to sync your Iceberg, Hoodie, or Delta tables across many different catalogs. So say I'm using something like Hive Metastore, and I want to have those same databases and tables reflected in something like Glue or Lake Formation. So we've already implemented this, but we're looking to add more catalog support, so things in the Snowflake and Databricks ecosystem. And similarly, once you've synced your catalog resources, the next big question is how do you actually enforce governance? So each of these catalogs has their own unique way of representing permissions. So things such as being able to grant a particular role or user the ability to do maybe a select query, so only having read access, or maybe only letting some people have the ability to write in terms of granting them an insert or update permission. So there's an RFC right now that anyone can go and actually read to see how we're trying to map out this internal model. Final thing I'll talk about very just briefly is just merge on read. So these table formats have two core concepts. One, which is copy on write. Essentially, when you make a change, you will basically version or recreate a Parquet file. But the merge on read concept is essentially, it's very expensive to keep recreating these Parquet files. So rather, let's keep the actual appends, like let's say delete, for example, in an auxiliary file. So for Hoodie, there is a log file, which is Avro based. For Iceberg, at least in the V2 spec, it was positional deletes, which would basically be an additional file, a delete file, which would keep track of the ordinal as well as the file path, so that you can at read time be able to stitch together if this record is actually needed or not. So being able to now convert these additional log or delete files is the next step, since you already have copy on write supported. And then eventually also adding support for other table format projects. So yeah, we really are looking for people to come and join the community. And these are the current contributors across many different organizations, OneHouse, Microsoft, Snowflake, etc. So, a big thanks to all the people across the industry that have currently contributed to XTable. And then special thanks to Kyle Weller and Dipankar for helping out, with this talk. So thank you, everyone. I'll be passing now to Anand for the second part of this talk.
While we get that, I'm Anand. I'm from the OneLake team in Microsoft. It's just great to see you all here. And I think welcome again on behalf of Microsoft. It's exciting to be part of this community and hosting this event.
What's up? I just want to see if we can get PowerPoint up.
Okay.
Oh, it's going to go through the whole entire.
Got it.
Okay,
there you go.
Right there.
Can you just present? I know, but I need to share. You stop sharing.
Still share or no?
Not yet, I think. Where is it actually going?
Oh, we have to go back on.
Okay. I just there.
Technical report is very hard even for software engineers. This is probably the hardest part of the talk, to be honest. It's good now. It's good? Okay.
Okay, there you go. Great. Okay, so I'll start now, family. Rahil talked about XTable, what it does. It's a great way of transforming between metadata formats because data is the same. You just want to use it in a different way. And now I'm going to talk about what OneLake does. So we use XTable. In fact, we also contributed to XTable. And it is better. Okay. So what we want to do, again, is emphasize this interoperability, right? We want to have the ability to let our customers have the flexibility to choose whatever engines they want, whatever is best for the job that they want to use it for. And we don't want to have analytics engines, to have to worry about which format they're working with, right? Now, in the real world, this data is somewhere, right? And we have to somehow get access to the data, have to show it up in the right form, and make this whole business of transforming, etc., seamless. So, okay, here's just an example of what we want to do. There is an Iceberg table, table A, lying around or floating around somewhere. We have Microsoft Fabric, wants to read this data, and then analyze it. We do something with it and transform it and then create another table. Fabric works with Delta, so it writes down a Delta table, that's table B. And then we have Snowflake. Snowflake wants to read the data in Iceberg form again. Right? So we really want to build these flows where the engines are agnostic of what the original form of the data is. So now we come to OneLake. OneLake is our SaaS data lake for entire organizations. So just like OneDrive is for documents, OneLake is for data, right? And the job is to abstract away the entire data layer. Right? You talk to OneLake, data can be there or data can be somewhere else, and you can bring in data through shortcuts. We'll talk a little bit about that. But originally, OneLake started with the Delta Lake format, right? And now we're adding Iceberg format. Okay. So here's a view showing some data lying in some storage. Where is it? It could be in a lot of places. It could be in OneLake itself, could be in Azure, could be in S3, GCS. That also doesn't matter, right? You can see that there's an Iceberg table, you have a data, and then you have metadata. Metadata has the metadata JSON files, arrow files, etc. How do we bring this into OneLake? We create a shortcut in OneLake, which just points to the Iceberg table, right? Important to note, the data is not being copied, nothing's being copied, but you have a way to access that data from within OneLake. The extra thing we want to do now is to add another layer here, because the original data was in Iceberg format. We convert it, it becomes Delta. Anyone who accesses this table through this shortcut should be able to consume it in either format. Okay, so what all do we have to do? How do we get this done, right? OneLake is the abstraction layer, so it has to know where each piece of data is. It doesn't matter where it is, as long as OneLake knows. It has to understand metadata formats, and based on who's asking for what kind of metadata, it has to convert it. So here's some table in Iceberg format. It's in OneLake. Somebody's asking for it. Some Microsoft Fabric engine is asking for it, but they're asking for the Delta log, right? Because that engine only can read Delta. So what do? We detect that it's an Iceberg table, convert it. This is where we use XTable to convert the data, and then send back the new log. It's another important thing here is the original table, this Iceberg table that we saw, we might not own it inside OneLake, right? So it is somewhere. We don't modify the original location, right? We built this whole abstraction layer of building a Delta log is on top of that, and it's transparent to users. Now, in any real system, live system that is scalable and enterprise level, there will always be trade-offs, right? So here are the kinds of things we need to think about to actually build a real system. There is consistency. Do you want to, every time somebody asks for data, do you want to give them the exact same data in both formats? Or is it okay to be a little lax about it? How fast do requests need to be? Generally, in a real system, you want requests to be pretty quick, right? And optimize for that. We could be highly efficient and do things only when they are required to be done and not do anything extra. Or we could do things which are not required, but might be required in the future, just anticipating, right? So there's a scale there. And then all of this usually has to be done at high scale. So this is just the kind of things we had to think about. And I'll show you an example of what kind of, how to slide the scale, and then what does that mean? For example, if you want it to be highly consistent, but also efficient at high scale, then maybe you can be mostly consistent, which means that you can allow a little bit of staleness, but not too much, right? We have to scale this horizontally. There'll be lots of different engines, lots of different clients asking for the same data or different data lying all across in different storage. And so this is where the work comes in to take something like XTable and then scale it out. And here we have to be, it has to be stateless. It has to be, there are several things, assumptions that you might get away with if you're running it on a desktop that you can't do anymore. And then finally, if you have, when do you want to convert, right? Do you convert every time somebody asks for the data, or do you can keep it converted whenever something's written? And can you do that or not? For example, if we convert every time somebody writes to it and nobody's asking for this, then we do a lot of work where it might not be required, right? So that's the difference between make on read and convert on write. This is kind of similar to what Rahil talked about in case of merge on read and copy on write, something similar. Okay, there are many challenges. I'll just point out one. More things that we have to do or we have to think about. One of them is the portability of Iceberg files, right? Iceberg uses absolute paths inside the metadata. This means that if we point to something from a shortcut, the metadata files in the region where the grayed out part is actually referring to the data not through the one lake shortcut, but it's directly there, right? So it still can't be used directly. It's something that we need to solve. Okay, so all that was talk. Now time for some demos. This is actually working in production. The first thing we do is we want to go to Snowflake and have Snowflake write some data in Iceberg format. So all this is just getting a path from one lake and putting into Snowflake so that Snowflake knows where to write the data to. We're creating a table. This table will be written into one lake. Okay, it's done. Then we add some data to the table. And then we go back to one lake. Going to one lake, this is in the files section. This is just a restriction for now because you created in the file section. The table section is structured data, right? But in the file section, you see that you can see everything that Snowflake created here, the Iceberg metadata. Going back, now you create a shortcut. Shortcuts can be to many places, but in this case, it's inside one lake, right? And you go to where do you want to create the shortcut to? That's where the Snowflake data exists. So we create a shortcut there. And okay, so here's the part. Now we see a table here, right? This table, whatever we are presenting here is reading it in delta format. So it's already used the original place. It used XTable, converted the data, and now you can see it in delta format. Okay, we can run some queries on this in Fabric right now, right? And it should all work. It refers to the original data. There's no data movement. We are not also adding the generated delta log in the original place, but to the engine who's asking for this data, it all works, right? It all seems like it's a delta table. Okay. Again, accessing it through one lake, we get the table. We can also generate Power BI reports using the same thing in Fabric. Anything that you can do in Fabric with a delta table, you can do this with this table, which was originally created in Iceberg format, right? Now we go back to Snowflake and try modifying some data. So we're adding a lot of files. What happens? Then we should go back to one lake. And once it's done, you'll see that the updates are now visible in one lake. Right? Refresh the data, see the new data. There you go. So behind the scenes, it's looking at what is the latest data available in the Snowflake, in the Iceberg format, getting the equivalent, running the XTable, all that. This is just to show that shortcuts can be created to many different places, right? We talked about S3, Google, OneLake, etc. And this is an example to show something in S3. So there's data in S3. We create a shortcut in OneLake to that data. The same thing, nothing changes. If you access it through OneLake, it still seems like the data is here. You can see it and can load it up. Okay. If you view the files here, again, you see the delta log, right? But if you go back to S3, there's no delta log there. It's just the original format. It's an extra layer that we add on top. And I think that is it. Thank you.